Work things out. So we're not necessarily here to solve everything or provide answers, but just provide an opportunity for people to think, ponder, figure out. Yeah.
Brilliant.
So how did you learn about the meetup?
I had been using meetups for local events, like before the times of COVID, and I had stopped even looking at the site, and then someone just like offhandedly mentioned to me, yeah, like meetups from around the world are happening over Zoom, and whatnot. And I says, of course they are. Of course they are. So I just went on and I searched by things that interest me, So here we are.
That's very nice. That's very nice. Welcome, Arthur.
Hello.
How's it going?
Pretty good. Let's see, we have a new member.
Hello, Arthur.
Hello.
Call me Chris.
Chris, nice to meet you.
Pleasure.
Chris, where are you connecting from?
Somerville, Massachusetts. That's around Boston.
Okay. So is that like a suburb of Boston or a little further out?
Neither.
Okay.
So Somerville and Cambridge are on the other side of the river from Boston, and the culture and the feeling and the whatever, it's much more akin to Cambridge than it is to Boston. So the taste, if you will, the culture is different over here.
Okay.
By enough that I care, right? And it's not a suburb, although Somerville is one of the densely populated places in the U.S.
Oh.
There are a lot of three-story walk-ups, and they're close to each other, and it's just like lots and lots of people per square mile.
Okay. Well, I'm in Manhattan, and Arthur is also in the New York City area, Yonkers, I believe. That's still true?
Yep.
Okay.
Yep, go Yonkers.
Great. And we do have a couple of other members who are pretty regular, and they did RSVP today. So yeah, hopefully they will join. And then we've had like 1, 2, 3 people join in and drop off. And so even last weekend, we had 2 new people. I don't know if they'll join again, but.
And last week you didn't have me, if I recall correctly.
Oh, that's right. You missed last week. Yeah, last week was actually a little dense, the material, unexpectedly. So I'm sorry?
Was that more trees or what was that?
It's still more trees. And most of the section was really just this program to do symbolic differentiation, to compute derivatives. Using a tree representation of an algebraic expression, a formula. And it turned out to be pretty involved. And it also turned out that unlike a lot of other programs that we've seen before, most of the pieces were actually in exercises. So we covered a little bit, but I'm not sure if we covered enough, to feel like, oh yeah, I have a good handle on this. But the core algorithm was quite interesting in terms of the way it represented the formula, and then in the way it was computing the derivatives. And more, what I'm seeing also in this section that we're going to study today, I feel like there's a lot of stuff in here that is coming from his background in compilers. So there's data structures, the examples, the applications that he's presenting. I feel like this is stuff that he was planning for the later volumes entirely on parsing and compilers. But yeah, it's great preparation that way.
Yeah, there was the interview that I posted 2 or 3 weeks ago where he had said sometime in the past few years that this actually started as someone came to him and said, let's write a book on compilers, or, can you, Knuth, write a book on compilers since you've been doing so much with compilers? And he said, sure, I'll just write everything you need to know to do a compiler. And it turned out that that was a lot more than he bargained for. But it was originally conceived as like how to write a compiler, starting from the basics.
Right. So I had a little communication with Alan Kay, 6 months, a year ago, because I was interested in doing something. And he reiterated himself, like he said this several times, is that you write the language you want in the language you've got. Okay. Right. So in that sense, everybody is writing compilers all the time. You're translating from input to output, and sometimes the input is the formation of how you want to be able to write programs.
Interesting. Yeah. And I guess another takeaway is that the field of compilers seems to encompass the entirety of computer science in some sense. Like there's just a lot of stuff depending on how deep you want to go into the details. A lot of opportunities to apply different data structures and algorithms and I guess language and formula representation techniques. Yeah.
Well, and here's one way I like to think about it. Okay, so you've got a new level of abstraction. How did you get there? You're writing a new language. That's how you got it, right? So.
Yeah, no. Well, this came up in one of our very first meetings, months ago. Because my background is, I got into, like, my first job out of college was writing compilers, working on compilers. Like, well, they're already written, right? Turns out that the stuff you learn about in compiler books or in college doesn't matter to industry because they've already got their compiler. So it just sort of naturally made sense to me that, like, of course, the last thing you build up to is the compiler, right? What else could there be, right? But as I've gotten older, I felt like there is more stuff out there. I'm not sure that I know exactly what it is, but there's whole collections of computer sciencey things to build up to these days that maybe didn't exist back then, or maybe did but weren't as sexy. But you've got graphics, you've got all the cryptographic stuff. Those have been around for a while. Machine learning type things, and none of those are exactly, like you could write a art of computer programming building up to, network protocols that might look very different from this one building up to compilers. But I wouldn't be qualified to write any of those.
Okay, so we are almost at time. Let us start in a minute or so. Here's what we're going to do today. So we are on volume 1 of TAOCP. And this is the 3rd edition. So that has been a somewhat, minor source of annoyance for some people, because a lot of people, it seems, do have earlier editions that they've kept. So, and the place where it becomes a little problematic is because I'll have slides up that'll say which page numbers we're reading and what the text snippets are that bound the reading. And sometimes, for people with older editions, that gets a little problematic. So I don't know if you're in that boat, but if you are, just let us know, and we'll try to help you find the right place. The other thing is that in addition to the third edition of this volume, Knuth, as you may know, updated his computer that he designed for the original edition, which he called the MMIX. And the updated version is called the MMIX. And while the texts themselves have not been updated with the MMIX versions of the code, he did put out a separate little booklet called the, well, actually, he didn't do this piece, but he collaborated with another person and they put out what's called the MMIX Supplement. So it has all the code and computer-related or architecture-related differences in this little volume. So we're using both side by side. As it happens today, we won't need the MMIX supplement. I didn't find any material that had a different version in there, so we'll be just sticking to volume 1. And currently we are in chapter 2, and that's the part of the section that we're covering, 233, and I've got the page numbers over there. But as I said, I will put up slides with the exact page numbers of what we're reading. Hi, Michael.
Good afternoon.
I think your video is frozen, but your audio is coming through.
Oh, let me allow the camera.
All right. That makes sense.
It's sitting there. Do you want to allow the camera? There you go.
There we go. Now you're moving. Now we're moving. So we have a new member, Chris, as he prefers to be called.
Chris.
And he's joining us from Somerville, Massachusetts, which I understand is very close to Cambridge.
Which is very close to Boston.
Very close to Boston. Okay, so this will be the process. We just read a couple of pages at a time, enough for about 5 to 7 minutes. You'll have a slide showing what parts you're reading, and as you read, please enter any thoughts and comments into the chat. That's highly encouraged. And then when we're done with the reading portion, then we'll open it up for discussion. It generally doesn't have any time limits, but we want to stay a little reasonable and not get stuck on anything for too long. We'll go over the chat, we'll discuss things aloud, and then the recordings are posted to YouTube, the chat, and any other notes and programs and code are posted to our GitHub repo. So let us begin. And so that's where we are, section 233. And we will read till about 219. Okay. Do we need a bit more time to read this, or okay to discuss?
About 2 minutes, please.
Okay.
I'm back.
Okay. So could someone just summarize this representation, the pre-order sequential representation, and anything interesting you care to comment on?
Well, this makes a correspondence between something we saw in a previous week, the pre-order traversal, and the storage order here. So that's a connection.
Yeah, yeah. I mean, it's something that would be interesting to use as an input representation as well, right? So if you had that kind of the pre-order, if you just say, okay, input the tree in pre-order, and then I'm going to store it like that, that would make the storage pretty straightforward.
He took away the RLINK in the tree representation, and instead he has this tag. Well, the RLINK, what the node that would have been pointed by the RLINK is the next one in the list, but there's a stop tag like by B that says that that's a terminal node. It doesn't have an RLINK, and so the next thing that happens is the C is really what's on the RLINK of B in the transpose diagram, which would mean that C is a sibling of B, and which would mean that it's an RLINK of A.
Michael, can you also explain that last paragraph where he says that the RLINK field itself is almost redundant?
The RLINK field is almost redundant. That was the. So are you talking about diagram 4? How he got to
diagram
that?
4. Diagram 4.
So in diagram 3, you have these arrows going to the where the RLINK would have gone to, like A to D and B to C. But if you really wanted to, you could get rid of the address and just have a bit there that says I'm where like on on node C there, it says I'm where the RLINK would have pointed to, but it doesn't. It's really kind of complicated to figure out that B would have an RLINK and therefore it would be pointing to C, and then the next one that has an RLINK is K, and that one, no, K, not K, because K is the terminal node, I guess. I don't know. The A is going to point to D. But it's hard for me to figure out how you go backward to get that. I believe it, but
Yeah, how would you follow the R-link, the missing R-link?
Well,
I think it's a sort of a brace matching operation-ish. Like the R-link in figure 3, where it goes, the first R-link goes from A to D, skipping over. By the way, I'm getting some echo from somebody.
Let me mute. Okay, I've muted.
Sorry, Taj, just other ones. No, still happening. I don't know. Okay. So in figure 3, we have an R-link from A to D, which graphically in the diagram is passing over 2 brackets in the LTAG column and 1 arrow in the R-link or row rather. And then the R-link edge from E to F is skipping over just 1 bracket, and from F to G is skipping over 1 bracket. And I think that in general, any R-link edge is going to have to skip over K other R-links and K plus 1 brackets, if that makes sense. So you can do a sort of a brace matching.
What does he mean? What does he mean by? I think it's the second or third last sentence in that paragraph. Each time we pass an item with LTAG equal to that stop symbol, we should complete the most recent instance of an incomplete R-link.
Well, that'll do it easier, won't it?
So he is suggesting that there is some additional data structure that you keep, right? It's not, you're not encoding everything in the representation itself, but when you're traversing, you need the help of a stack. I'm not 100% sure how that's going to work, but that's the sense that I'm getting.
Yeah, absolutely. And so you're pushing it equivalently. You're pushing and popping on the stack.
yeah,
right? So you're matching brackets, so to speak, in order to get to the one that you actually want to use, and you have to do a complete scan through the data structure using this system, right? So.
Well, it doesn't have to be a complete scan.
No, wait, hold on.
You can go through a subtree, okay?
No, I'm sorry. I went on the paragraph. They're only redundant if you drop a few and scan through the whole thing, and I don't know how you do that, but that's the next section, right?
Okay. So let us continue, because I think he does explain it a bit more, not completely, but I think we will get a better sense of what's going on. So this is the next couple of pages, just where we left off on page 349. And then I've got a couple of snippets at the bottom of the slide. The first snippet is where we're going to start the reading, the fact that RLINK or LTAG, etc. on page 349, and then the second bottom snippet is the end of the reading on page 350. Okay, does it make more sense, or at least we find like the RLINK really isn't necessary, could be used for other purposes?
I don't think he's saying the RLINK is not necessary. I think he's saying when the RLINK is empty, you could use that empty field for other purposes. Or you can get rid of the RLINK by having those special link nodes, which you're adding memory to for the special link nodes, but you're taking away memory on more than you're adding in the second example.
Yeah, so that part seemed a little more straightforward to me. I can see the trade-off over there. So instead of having that field in every single node, maybe just have them once in a while as these extra nodes. Not sure how exactly that's going to work.
Number five, he's not taking away the R-links. What he's doing is there were many nodes that had no R-links, so they would have that lambda for the R-link, and he's saying, instead of just wasting that memory, let's use it by having this pointer to the next subtree beyond the tree of influence, beyond the descendants of this tree.
Figure 5 makes a lot of sense to me. I think 5 makes way more sense than the RTAG LTAG business to me.
What does?
I think that's the figure 5 with the scope fields, because then you don't need any of the L or R things. And if you want to traverse the tree, you just say, well, my leftmost child is start right after me, and to get to the not quite leftmost but almost leftmost child, my second child, then I ask my leftmost child, what's your scope? And I skip over all them, and the one right after that is going to be my second child. If I want to get to the third child, I ask the second child, how big are you? And skip over all that, and that's my third child. And I can iterate over my children very quickly that way. And if I want to go to my sibling, that's a linear time operation, or that's a constant time operation. Because I just look at my scope and skip over me.
Yeah, the scope of X equals X plus C, that seems very attractive. Any other questions or comments? Has any of you ever used any of these alternative representations, or could think of applications where they might provide some benefit?
Well, one thing to keep in mind here is that this is general trees, right? Not binary trees. And I personally haven't had a lot of use for general trees to begin with.
Yeah, that's true. These are binary tree representations of general trees.
One way to think of the difference between 5 and 6 is 5 is speed and 6 is space. So there's a certain amount. You're compressing in 6 versus you're getting optimizations for certain characteristics on 5.
Yeah.
Well, 6 is adding those fake nodes, the stars.
Right, so but only when necessary. So it's taken away all the ones that are unnecessary.
Yeah.
So that's why
it's just another representation. I'm not sure if the nodes were very large, 6 might actually take more memory. You don't know the size of the node versus the size of the RLINK pointer.
Yep.
You're adding RLINK pointers, but you have if this is going to be a linear representation versus a sequential representation, then point taken. If it was like a sequential representation where the stars only take the number of bytes that they needed, and you're going to read it sequentially instead of indexing into it, then yeah, that works.
Yep.
That works to save space. That's probably actually the way it would be used.
Well, it would have to be because the size of the things in between the pointers vary.
Well, not in the MMIX representations. In the MMIX representations, these are all probably octas, which is eight bytes. Yeah, that's just.
Well, no,
that's what I was thinking. That's what I was thinking. I was thinking, you know, A is taking up an octa, and 2 of the bytes in that octa are a pointer that you're wasting. So instead of using that, you're going to have a whole nother octa for this star that's only going to have the pointer.
Right, but you still can't. Oh, I guess you can index because the pointer is pointing the index, but you can't index from the front because you don't.
Yeah, that's why it's only 16. That's why it's only 2 bytes instead of a whole.
Well, no, but that's why it's only viably doing sequential. Right. 6 is only viably doing sequentially.
All right.
I don't think that's true. I mean, and
okay.
So, Chris, in your interpretation of 6, you had said that maybe the letters and stars were variable width, and
no,
I don't
even if they're constant, getting to your 8th data element isn't a simple arithmetic operation because the stars are there too.
Getting to the 8th element
from the start. Let's say you want to do random access, right?
When you say 8th, you mean 8th in pre-order?
No, he means...
Well, 8th in representational order. But yeah, you're walking the tree. You're not actually... Never mind.
Yeah. If you wanted to get to the 3rd element in 6, if you wanted to get to the 3rd element in 6, you would get to the star. And what you really want to get to is the C. So how do you do that? How do you do that? Well, it's not really indexed anymore, but I don't think the point of 6 is you're taking away the indexed part of it, right. and you're so that would mean that the star could take, star would just be an RLINK pointer. Maybe it's only 2 bytes. Well, maybe 2 bytes.
You still have to, since it's a tree, you still have to follow the pointers in which way it is.
Exactly. Yeah.
Well, now that I see what you're saying, though, I'll flip the other side, be the other devil's advocate here. That it's not usual that you want to say give me the 8th element. Like, it's not a random access container, really. You don't want to say give me the 8th element in the tree. That doesn't usually make sense. Right. There are definitely cases where you might want to say I'm going to do something to all of the elements in the tree, and I just want to go from the first one to the last one. It doesn't matter the structure. I'm just multiply them all by 2, or update the position of all the monsters, or whatever it is. And there, it might be useful to be able to reuse your iterate over a linear array code and not have to write special code for iterate over a linear array, but skip some of the elements. So that is a benefit of 5 as opposed to 6, that 5 comes with this nice in-order array that you can iterate over without skipping anything.
Okay, great. That's yeah, go ahead, Michael. Did you have something?
No, I'm saying maybe. I'm just saying maybe. It's too abstract. It's too abstract. I can think of, I mean, how often do you want to go and iterate straight through on it? If it's a tree, the reason why it's a tree is that you're going to take some of those branches. And on either 5 or 6, you've got the arrows, like if you are looking at A and you decide that A is irrelevant to your task, you'll want to skip to the RLINK and skip to D. Either one of these lets you do that. But you're right. You wouldn't. Your point is taken that you wouldn't really want to be able to randomly access one of these things by its index. Like you wouldn't want to say, okay, what's the 3rd node in this tree representation and come up with a C. That doesn't make sense. I mean, maybe it does. Maybe it does in some contexts. I don't know.
It may make sense if you knew you had a complete, like a full binary tree. Somehow, your data has been arranged in a way that it is like that.
Yeah, there could be.
Yeah,
that could be. I think. Okay. All right.
Well, if you have a full binary tree, you don't need either 5 or 6.
Exactly. You just
Right.
lay them out
If you
sequentially.
know you have one, right?
Yeah.
Yeah, that's true. I was just saying that you could imagine some sort of random access application even with a tree in that case. But yeah, let's continue. So we're just continuing from where we left off, but we will stop just before the middle of page 351. So before the algorithm itself. Not a lot of reading, just 5 minutes.
Family. What is it called? Family.
Okay, so I think it's referring to the family tree that was covered early on in that first section on trees. And but if someone can explain it.
Yeah, I think I've traced through it, and I think when he says the family of the most recently appearing node whose family has not yet been listed, I think you can replace family with collection of descendants.
Okay.
So we've got a sort of a stack going on in figure 7. So I drew out the same thing that's in figure 2 on page 349. If we look at the right-hand bit of that, so that's the binary tree version corresponding to this set of set of trees, this forest. And we start with listing out the roots. So we have A and D. So those are our patriarchs of these families. We got A and D. And then we have an R tag indicating that's all the patriarchs. And then we start, we've pushed these onto a stack that we are now going to deal with. So we have to deal with A and D, but we're in reverse order. So D, what are the descendants of patriarch D? We have E, F, and G. And then we're done, R tag. And then so now E, F, and G are all on our stack. So what are the descendants of G? Nothing. What are the descendants of F? That would be just J. And then we're done. What are the descendants of E? That would be H. And we're done. And now we're done with D's family. And now we pop that off, and now we're back to talking about A's family. So A has descendants B and C. And C has descendant K. And then we're done with C, and we're done with B, and we're done with A, and we're done with the whole thing. So we build it up in this sort of stack approach. And I did have this example and confirmed that of course, he's right when he says this is the reverse of postorder. I haven't figured out what this is good for, but I managed to trace through it.
So is it literally the reverse, meaning that you write it out in post order and then you just reverse that string and you'll get a string,
That's
the
right.
string in 7?
That's right. If you take the figure which you've got on the screen right now, and sort of tilt your head 45 degrees toward your left shoulder, if you were going to run post order on this, that means you visit the left children, then the right children, then the self. So the left subtree and then the right subtree and the self, right? So post order on this tree would start KCB, because that would be the left subtree, and then the right subtree is more complicated, but it would start with H, and then J, G, F, E, D, A. And if I did that right, that is exactly the reverse of figure 7.
Okay, that helps
So
a lot.
What does the term family mean exactly?
I don't know exactly, but if you take it to mean collection of descendants, it all makes sense to me.
So in your interpretation, the family for A would be all the descendants of A, B, C, and K?
Yes.
And D and A are not in the same family.
Right.
But he says that 7 is in family order. Which to me, the way I got the interpretation was family is all of the siblings. So A and D come together, and then E, F, and G are siblings, and they come together. H and J are they're not siblings, but they're singletons, and then B and C come together, and then K comes by itself.
I think Michael, you're right, because he does say that the R tag, the bottom stops, serve to delimit the families.
There you go.
And he also says,
why didn't you call them siblings then?
That's a good question.
That's what they are. They're siblings. They're the siblings.
These are very nuclear families.
Yeah.
But yeah, he does say above
No
also
divorce is allowed.
the members.
No divorce is allowed until Section 4.
All right. So who wants to give a shot at explaining level order?
Oh, I didn't even get there yet.
Oh, okay. Should we spend another couple of minutes reading?
Yeah.
Let's do that.
How far are we going here?
Just till where it says another sequential method. So it's like one paragraph, really? 2 paragraphs?
Okay. I guess I got that far.
Oh, okay. Yeah, I think that's all he's given for level order.
Yeah.
Go ahead, Michael.
No, level order is just those numbers are just the number are just the level of the level of the tree in terms of the number of descendants. D on the right hand actually does have 3 descendants. They would be E is at the first level, F is really at the second level. You kind of have to turn your head 45 degrees to see that, because to remember these are binary trees. E and G is at the third level.
Yep.
And it's got a pretty clear analogy to the other representations where I think where the numbers change, that's where the stops are.
Yeah, where the level, no. Yeah, so the stops are...
So actually, the best way to think of this, I believe, is an analogy to the one we just looked at. So it's the order of the siblings that you go in that's changed here. It's which ones, if you've got a set of them, which one goes first, if you will, is the way I'm reading it. So instead of
oh, I see what you're saying. Yeah.
Just to be clear, we're talking about figure 9 or we're talking about figure 8?
9.
What? Oh, there we go. I thought Michael was talking about 9.
I'm talking about 9.
Oh, okay, got it.
Figure 8 is just read off line by line in the tree. It's if you had a nice binary, a complete binary tree, this would be the order that you would put like a C++ priority queue.
Right.
Order is all 8 is.
That's all that 8. Yeah, that's right.
But how do you explain the stops, the R tag values?
Right. So just read the paragraph after. Oh, I'm sorry. I'm not on mute. The paragraph after the diagram, he says that it's just like 7, only you're flipping each time you go down.
Yeah, exactly. Those stops are still the ends of the families. A and D are in the same family. B and C are in the same family.
Okay. Okay, great. So let us now look at the algorithm, which has a different sequential method that I think Michael was talking about earlier, called post order with degrees. So there's that introduction, and then there's the algorithm till the end of page 351. That's it.
Oh. No, this algorithm is evaluating a function once you already have that representation. It's not creating that representation.
Correct. Yes.
Right, it's traversing the representation.
It's saying that representation is used for nested function calls, like the kind that you hate when somebody else wrote it and you have to debug it. You know, where you say foo of left paren bar of 2, 3, zad of 7, 8, delta of 9, 10 with all those parentheses. And you need to evaluate a function where, go back to that diagram, A is...
Yeah, figure 9 is sort of like if you took the original, the left-hand side of figure 2, the original trees, and you treated these like expression trees and represented that expression in Polish notation. Right, where you're sort of pushing, so that this would be A of B and C of K. And then D of E of H, F of J, and G. Right? And then algorithm F is basically saying, how would you evaluate that using a stack? And then using the representation from figure 9. And the representation from figure 9 is exactly just the Polish notation of the expression. So it's saying, push B on your stack, and that's going to be one of your operands to A as it happens, but we don't know that yet. And then push K, apply C to K, because C is a function of 1, degree 1, right? Arity 1. So now we have B and we have C of K, and those are, and then we encounter A, which is an operator with arity 2, and we apply A to C of K and to B. And that gives us a new value. And then we also have H on the stack, and then we have E of H, and then we have J, and then we have F of J, and we put G on the stack, and then finally we have D of those last 3 things. And we end up with 2 values on our stack, which are the evaluated value of A and the evaluated value of D. And we can do all of this just by getting the operands in that order and knowing the arities of all of the operators.
I think you just described algorithm F.
Yep.
Yeah. And it seems really efficient and very straightforward.
It also handles functions that have 3 arguments or more.
But it requires you to write your expression in this Polish notation, where all of your verbs come at the end.
Yeah, but
that's just a parsing problem. Come on.
That's a parsing problem. Yeah, exactly. It is, actually.
That's just a translation problem.
Well, you got to do both.
You have to come up with some representation anyway, so you might as well.
I mean, if you're thinking of a programming language, then your function names come first. So you're in prefix order. You have to translate that into something that you can use to evaluate.
Right. Well, I particularly like Forth, and it's a stack machine where you're doing essentially exactly this, and you keep on putting things on the stack, and then the operator takes it off the stack, right?
Right. And who's to say that your functions are functions the way we would write them in a program? They could be operators like plus and minus and times. That's infix. Whatever it is, you're going to have to parse it. It's a parsing problem, just like you said. Whatever it is, you're going to have to parse it and come up with a tree like this to evaluate. Well, maybe there's other ways. There's probably lots of other ways of doing it, but he's showing how to use this level. What did he call this?
Postorder with degrees. But the trick about this one is that this is not an algorithm on a tree. This is an algorithm on a representation of a tree. It only works if your tree is in a specific linear representation, which just happens to be the form you would get it in if you were a Casio calculator, but not if you were 83, right? So maybe
Well,
there's
I
a
mean,
problem.
I mean, if you're writing a compiler, you could generate this kind of structure and use it this way.
Yes, but you'd need an algorithm to generate it.
And if you were writing forth, you just have to.
You don't do anything because this is the way forth looks.
Do you
Right.
happen to know if Forth is using this sort of internal structure?
Well, forth uses kind of.
Kind of,
No,
yeah.
no, the
It's
numbering,
kind of. I mean,
the numbering, no, it uses a standard stack thing where it's
Yeah,
pushing
but-
and popping. It
but
may.
in Forth, your Atom D would consume 3 things off of the stack.
Yeah, I don't know what the on disk format of compiled forth looks like, and it very easily could look like this.
Yeah, there isn't a compiled version for Forth. It would be opcodes in this order. That's exactly what it would look like.
Well, another famous stack language is Postscript, and I wonder if it does something similar.
Postscript?
Yeah. Postscript for page layout.
For page layout, but that doesn't use those numbers either.
Now, who knows what the internal saving of the stack, what programs look like, if they weren't purely text, right?
But in Forth, I don't think you're going to have those numbers in the internal representation. What you have is a word.
Well, I'm tempted to write a Forth compiler that does exactly this.
That would be very cool.
Because then you just load it and it's runnable. Almost, you don't have to parse any characters.
Write it in MMIX.
Okay, so we are a little past 3 already. Usually we just take a 10-minute break around this time, so that's what we'll do.
Okay.
So the meetup will stay up. Feel free to turn off your cameras and mute your mics and go refresh your coffee or whatever. So we'll see you at 3:19.
Alrighty.
Okay, we are back. Whenever you get back, let's continue on page 352 and page 353. Okay, who could explain the linked representation? I guess there's more than one. There's at least two.
Okay, I'll go. So the first one he shows in figure 10 is basically taking the A that had been at the root of the left tree and bringing it down to become the first child, so that all of your information goes into your leaf nodes, or terminal nodes, as he calls them. Why is that useful? Because your terminal nodes haven't got any link pointers, right? Both their pointers are null.
So you can reuse that field for either info or link.
Right. And then the other one he shows in figure 26 is
Could there be other benefits apart from just that reusability? It sort of reminds me a bit of B trees. Michael, you're muted, by the way, if you're speaking.
Anytime. Yeah, B trees commonly do that. And then what you have is you have a in this new representation, a node is either terminal with info in it and no pointers, or it's a parent node with pointers and no info. So they're actually more split out. And I've seen B trees that go both ways. Some B trees will have the data on the internal nodes, on the parent nodes, as like a normal binary tree, and a lot of times they'll put it so that only the bottom level carries the info.
So one impression I have is like maybe an advantage of B trees or the design of B trees is memory access locality, right? So if all the information is always sort of in some predictable area, then can you have like better performance in terms of cache hits?
Although one thing to watch out for here is that I don't know too much about B trees, but I think they look a lot like the drawing in figure 10. But the drawing in figure 10 is not really how Knuth is encoding this in the computer, right? He's still using the corresponding binary form, where there is an RLINK pointer in D, and in E, and in F, pointing to its right sibling. Right, he's got the L link pointing to the leftmost child, and the R link pointing to your next sibling.
That's a good point.
He talks about B trees.
Doesn't really have 4 children, according to the computer. It has 2 children.
I'm pretty sure he talks about B trees later, and 10 would not be a B tree because B tree is height balanced. So A and B are on level 2, and C and K are on level 3. And that's not balanced.
That's
so
another
if
difference.
it was B tree, they'd have to be brought down.
Yep.
And yeah.
Okay. What about the parent links and the triply linked tree? What did you get out of that?
The triply linked tree?
Figure 26.
So child links and a parent link.
I don't know what you're talking about.
Figure 26, is it not in your edition, Michael? Do you have a figure 26?
Aren't we on figure 10?
Figure 10. No, so that's more like, it's not called a figure formally. That's more like a diagram that has a 10 reference number, but there's a figure, like an official figure 26 on page 353, the next page.
Oh, yeah, so there is.
Yeah.
I will say that his style of having the numbered equations and the numbered figures sure made it tricky to find where with the figure. He said, look at figure 20, and I was like, how many equation 10s do I have to go past before I get to figure 20? It was a lot.
Yeah, I wonder what it took in his mind to elevate something to a figure, and something that's not as significant just got the equation numbering.
I suspect cynically that it had to do with which piece of software produced the image.
Could be.
Okay, well, that's just now we've got a tree with 3 links. We've got the left, and we've got the right, and we've got the parent. But parent is, in terms of the original tree, like G, the parent of G is D in the original tree before we transformed it.
Okay, so the very last sentence of the reading that we did, why then haven't we considered upward links much earlier in our discussion? Did you get anything out of that? The answer, of course, etc.
Well, pretty much just that you can't really do anything with the parents, because the thing about a tree is it has one root, and from the root you can get everywhere if you have downward links. If you have upward links, you can't get anywhere from the root.
Yeah,
and you could get from a leaf back up to the root. That would be cool, except that how do you get to the leaf, right? You've got a whole bunch of different leaves. So upward links don't help for navigating.
They don't help. They don't really. Well, they don't. Well. Maybe they do. And the situation where they do is where you don't want to use a stack, or you don't have a stack of how you got to that node.
Well, threaded links are kind of upward, right?
Exactly.
Actually, they're always upward. They're always upward.
Exactly. Let's say these were B trees, and you had 2 indexes, and you find a piece of information on one B tree, and now you want to find the next key relative to another B tree. You know where that node is, but you don't know how you got there. A parent link is very useful in that situation, because you don't need the stack anymore.
Okay, so right after that, he does say there is, however, a very important application, and that's what we're going to find out. So reading till 338.
And having skipped ahead a little bit, I think that the very important application he's describing here is union find, but he never uses that term.
Okay.
It's the union find algorithm.
Oh, where is it?
Okay, who could explain the problem? And is it what you think it is, Arthur?
Yep.
Okay, then maybe you could just explain this formulation and what you think is the same thing as union find.
So okay, so at the top of page 354, Knuth gives it in this weird integral way of looking at things, right? Saying like, let's suppose that 1 was equivalent to 5, and let's suppose that 6 was equivalent to 8. Using the same equivalent notation that we use for like equal modulo some value. And so it took me a little bit of staring at that to realize that these were not equivalent modulo anything. These are just random equivalences we're getting. And so I would think that if I were trying to explain this, I would look at flood filling an image, right? You have a whole bunch of points, or maybe you have identifying the connected components of a graph. You have a bunch of points. Some points are connected to others by edges. So you're given the set of edges, and you want to know what nodes are in the same connected component as this one. Right? Build me the set of connected components of this graph. Find out if there's a path from here to here. How do you do it? And the way we're going to do that is make an array with one element for each node in our graph, which in this case is the integers 1, 2, 3, 4, 5, 6, 7, 8, 9. And then for each edge, like from 1 to 5, take 1 and 5 and put them together. And the way we're going to put them together is we're going to pick one of them at random to be the parent of the other. We're going to say 5's parent is 1. And then we're going to say 6's parent is 8, and 7's parent is 2, and 9's parent is, well, also 8. So I said 6's parent is 8, right? And then, so I said 7's parent was 2. Now 3's parent is, and I could just say 7, but I'm going to go a step further and say that 3 is congruent to 7, so 3 has the same parent as 7. Like, find me the parent of 7, that will also be the parent of 3. So both 3 and 7 are now children of 2. And I keep going in this way. And if I want to find out at the end, like, are 4 and 9 both in the same connected component? I say, well, 4's parent is 2, and 9's parent is 3, whose parent is 2. So, like, okay, yes, they're both in the same tree, therefore they're both in the same connected component. But 1, on the other hand, is not.
Okay. Does anyone else have thoughts on how they would have approached the problem or a solution to the problem? Or if you've seen this problem before and a different solution to it, how is it different?
Yeah, there's one little detail that needs to be fleshed out yet. Like, let's say we started out and we said 1 is equivalent to 2, so we put 1 on top and we make 2 the child. The next one could be 1 is equivalent to 3, so we put 1 on top and now it has 2 children, 2 and 3. Now let's do the same thing with 4, 5, and 6. So we have 4 as the top and 5 and 6 as the children. What if the next input you read is 4 is equivalent to 2? That's 2 of the child nodes are equivalent. You got what Arthur said is going to work, but there's more to it than that. You can take 4 and put it as a child of 1, but now you've got to deal with the 2 and the 3 that were also, or the 5 and the 6 that were also equivalent to 4.
Well,
Okay.
the way that you deal with that You're saying that, well, now with 5 and 6, you have to go up 2 hops to get to the true root.
No, I'm saying we start off with, when we read the first part of our input, we have 1 at the top and 2 and 3 as children. And we have 4 at the top and 5 and 6 as children. And now our next piece of input is going to say 5 is equivalent to 2. Okay, you can deal with the 5 the way you said it. The way you said it is fine. You said that the 5 is equivalent to 2, but 2 is a child, so we want to go up and make 5 a child of 1. But you also got to deal with the 4 and the 6.
Right. We have to go up from both 5 and 2. Yes. So we go up from 5 here, and you say, okay, so 5, we're trying to make a link between 5 and 2. So 5's current root is 4, 2's current root is 1. We're trying to make a link.
I think you're missing the point. The way you described it works as long as the element that you're associating is not part of some other tree.
I am altering the description.
Okay.
Right, we're just adding an edge between the roots, right, of 2 and 5.
I don't want you to correct your algorithm. I was just saying that the problem is a little bit more complicated than that, because you might get equivalences in those pairs. You might get equivalent pairs way down the list that are joining not just simple items but trees.
Yes, and step 1 is trace them all the way up to their roots.
Both
if they're in the same tree, we don't have to do anything. Right. Step 1 is find the roots of both, and if it's the same root, you're done. And if it's not the same root, pick one and make it the child of the other. And if you want to be slightly clever here, I think you can count as you go up and find out which of these trees was deeper. And you can make the deeper tree the parent and the shallower tree the child, just to try to keep things a little bit balanced.
So it sounds like there's some merging of parents that's involved.
Aren't we keeping the trees at level 2? No, I guess we're not.
Level 2? Okay.
Aren't we keeping the height? Aren't we trying to keep the height of the tree at 2? I thought at first we were, but we're not. I mean,
it's nice if you can do that, but that is not a property of the algorithm intrinsically.
Yep, I see that. Yeah. I didn't read down that far.
I put this edge sideways, but really it goes one way or the other, right? Either 4 is a child of 1 or 1 is a child. And you can have multiple, more than 2.
Yep, got it.
Right? So here, let's say 1 has 3 children, and 4 still has its same 2 children.
Okay, got it.
Okay, let's now look at the actual algorithm, see how it matches up with our intuition.
Yeah, that's exactly what Arthur said. I guess the other interesting part of the algorithm is, let's take that same example. You got 1 at the top, 1 is the root, and 2 and 3 is the 2 children. And now your next piece of input is 2 is equivalent to 3. And in this algorithm, you're going to follow the 2 and the 3 up to the top, up to their parents, and they're both 1, and you've got nothing new to do. But it could have been that your input was 1 and 2, and then 1 and 3, and then 2 and 3. That's why that step E4 is important.
Okay, could someone walk us through the example right after the algorithm, labeled 15 and 16?
Well, I can do what everyone else does.
Thank you.
I was actually going through the last thing he says after that. The remaining relations are interesting. See exercise 9, and exercise 9 is do the remaining equivalences. And it was actually interesting because he doesn't get to the really interesting part, in my opinion. So what are we doing here? So we're setting, in each case, in each equivalence, you say 1 is equivalent to 5 means 1's parent is 5. That's the way we're going to join everything up. So the very first one is easy. We set parent of 1 to 5. That's all we need to do. We set parent of 6 to 8. We set parent of 7 to 2. And we set parent of 9. Well, we walk up from 9, we walk up from 8. Oh, 8 is already a root, so okay, so 9 gets 8. So nothing interesting has happened yet. And then we get the more interesting part. So we set 3's parent to 7. 3 is currently a root, and 7 is not a root, so we don't actually set 3's parent to 7. We go up to the root of 7. So 7's parent is 2, 2's parent, 2 is a root. So we set 3's parent to 2. Then the next one after that is 4 and 2. 2 is a root, 4 is a root.
Wait a minute, how did you get 3's parent is 2?
We trace up to find what components 3 and 7 are currently in, right? And
so 7's parent is 2 already.
Yep, and
Okay.
2 is a root. So 7 is in component number 2.
Mm.
And 3 is in component number 3. And we're going to join them up. We're going to make 3's parent be 2. And then with 4 and 2, they're both already roots, component 4 and component 2. Nothing interesting happens. And then 9 is in component 8. And wait. Yes, okay, so yeah, we're doing 9 to 3 now. So 9 is in component 8, 3 is
So
in component...
we're on step E3 right now. J is 9, K is 3.
I'll take your word for that, yes.
Okay.
So 9 is in component 8, 8 is a root, and 3 is in component 2, where 2 is a root, and we're going to make 8 be a child of 2, because that's the order they were given to us in. And so 8's parent becomes 2. And now the interesting thing about this is that now we have this diagram. So we do have some grandchildren showing up here, right? 6 and 9 were not modified by this operation we just did. But the interesting thing is that now if we added another node, we said, let's say 9 is congruent to 10, then we'd say, okay, well, 9 is in component 2, right? And in the process of finding that out, as we go up from 9, we're actually modifying its parent, right? 9's parent is currently 8, but 8 also has a parent. Oh, okay, so 9 can just move up. 9 is now a child of 2 directly. But again, we don't move 6 around. And so the act of adding an edge between 9 and 10 actually shallows the tree a little bit. So the tree can get arbitrarily deep, but even the act of adding this edge between 9 and 10 can actually cause it to get shallower as well, and so it tends to stay shallow. That's pretty much it.
Okay, that's great. How does that sound to everyone? Good, 2 thumbs up, excellent. So exercise 11 seem to be much more involved than just simply continuing this example. Am I looking at the right? Oh no, I'm looking at the wrong exercise. Exercise 9. Ah, yes. Okay. So exercise 11.
No, I'm confused. Yes, exercise 9. Yes.
Yeah, it is exercise 9. Yeah, so that's pretty much the topic for today. And we have a few minutes. So, if you want to try out a couple of exercises, generally we do attempt like the easier or at the most the medium level exercises. So nothing much higher than the low 20s in terms of the rating. So if something catches your eye, otherwise we could just start with exercise 1, page 359, which is asking, is it possible to reconstruct the L-links if we decided to omit them in a level order sequential representation?
Well, I have no idea how to actually prove this, but my intuition was, yeah, sure, why not? And the answer is, yeah.
Okay. So how would you do it?
Well, it's analogous to what we're doing in 3, going from 3 to 4, which is page 349. In figure 4, where we have just the R tags and L tags. Oh yeah, wait a minute. We don't have L links there. Isn't figure 4 what we're talking about? What are we talking about? Oh, level order, right. So anyway, in figure 4, if we had figure 4 and wanted to go back to figure 3, we would say there's an RLINK arrowhead on C, D, F, and G, because those are the nodes that immediately follow an R tag or an L tag field.
Mm-hmm.
And so in figure 8, the same thing holds. In figure 8, we know there's an L link down arrowhead on nodes B, E, K, H, and J, because those are the nodes that follow R tag brackets.
Okay, you're saying that they're almost not even almost, like exactly equivalent. You would replace the L links with the L tags, just like the R link was replaced with an R tag before. Is that what you're saying?
Yes, I'm saying that we know the arrowhead ends of all of the L links. We just don't know where the arrow tail ends start, which is what L tag would tell us. L tag is saying, is the L link null or not? So if we know where all the arrows start and we know where all the arrows end, I think we know all of the arrows.
Okay.
I guess that's not 100% obvious, because in this one the arrows are crossing over each other.
Yeah.
Right? With the other representation, they were nicely nested, and so it was very obvious that a set of starts and ends could be partitioned into a set of arrows. Here, that's not 100% obvious, but it works out somehow.
Okay. Any other exercise that somebody wants to discuss?
Well, number 6 has an arrowhead by it. It looks complicated, but it's supposed to be important.
Okay, let's just read through it and maybe somebody can just explain what the problem is. We don't necessarily have to come up with a solution or even attempt it, but what is the problem here?
This is exercise 6 on page 360.
Yes.
Hey guys, nice meeting. I'm heading out. You're scheduled for 2.5 hours?
We're scheduled for 2, but
Oh, okay.
you know, it's sort of like we definitely go on for 2. Often we'll go on for a few minutes, sometimes even a little longer. It depends on
even longer. That's what I'm hearing. Okay,
Yeah.
very good.
So next week, this is the agenda. Next Saturday, we'll be finishing up this section, and then actually, what's interesting about the following few sections on trees is that I noticed they're a bit more mathematical, but they seem pretty important in the sense that the concepts have been mentioned earlier, and then I have a feeling that they'll be used a lot in later parts of TAOCP. So we'll try one, the very next one, which is sort of like mathematical properties of trees, and see how people feel about it. So there's about, I think, 3 sections that are a little more mathematical. Then there's some more algorithmic stuff related to lists and garbage collection and multi-link structures, which may be like another 3 or 4 meetups at the most. And then that will pretty much complete the trees chapter. And then we have a couple of sections left over from an earlier chapter. We'll cover that, and hopefully in about 8 meetups or so, 8 weekends, we should be going back to volume 3. So
Got
that's
it.
the plan.
Thank you, and enjoy the rest of your days.
Thanks, Chris. Okay, so did somebody get what exercise 6 is about?
Yes, and it is interesting, and I have not figured out how to solve it, but basically what it's asking is design an algorithm where the input is a linked list of nodes, where the nodes just, they're just nodes, they've got some info in them that we don't care about, some payload. And then each node also has one, so they're all linked together in a linked list, but then each node also has a parent link. It says, this other node is my parent. From only that information, reconstruct the original tree. Just put them into a tree by repointing these links and get a pointer to the root.
So add child links where you're given only a parent link?
Yes, and you are given the nodes in some traversable order. They're all linked together in some linear order, so you can get
okay.
all of them.
So
But
that is known. What is that order?
No, you don't know. It's not level order. It's not prefix or it's just some random order.
Oh, okay, some order.
You're given a bag of nodes so that you can access all of them, but all they tell you is the parents. And so I see that you can find the root of the tree pretty easy. You just pick any node and just keep asking for its parent until the parent is null. And he's okay, foo, I found the top. I found the root of the tree. But of course you can't just take and repoint your first pointer up to the root of the tree immediately, because if you do that, you've lost half of your stuff. So you have to kind of start at the bottom. So you have to start at the bottom? And yeah.
If we weren't thinking about efficiency and we just, made like repeated passes through the entire list, sort of building up these child pointers every time we, came across a parent,
yeah, I mean, the result that you want to end up with, RLINKs normally connect siblings. So you do sort of want to sort the linked list such that all siblings are next to each other, right? Start with this guy and find everyone with the same parent and relink your linked list so that these guys are close together and leave them together.
So one question I have is he's mentioned the L child and the RLINK fields. Why is he making that distinction? Why isn't he calling it L-link? I remember reading somewhere earlier where he talked about the distinction between L child and L-link, but I'm not sure I got that.
Well, I don't think there's any real special meaning, but it's just that here the L child pointer is pointing to your leftmost child, and your RLINK is pointing to your next sibling. Right? So it's not like left child and right child. It's left child and RLINK to the next sibling, our sibling. And he's just given
so this is supposed to be that binary tree representation of a forest?
Yes. This is the same as figure 26, which is on page something,
Mm-hmm.
page 353. It's exactly what's on figure 26. Mm. We have L child and RLINK, and then we have the parent. And the parents are filled in for us. The L childs are all null, and RLINK is just some random order.
Okay, I think I understand the problem. Yeah, so the RLINK is basically initialized to just being used as a linear list, that's all. But then you'll need to change RLINKs and you'll need to fill in the L childs. And
right. And you can leave everything actually RLINKed together if you want, because now that we have the parent links, If you look at figure 26, the only place that RLINK is ever null is at a boundary, right, where the next guy over to the right has a different parent from me. Like C's RLINK could be left pointing at E, and G's RLINK could be left pointing at K, and K's RLINK could be left pointing at H. That wouldn't really affect our ability to deal with this tree, because we can tell that K and H are not really siblings because they have different parents. So we can use that to our advantage. We can leave everything RLINK together and just sort of permute the order of these nodes.
But the RLINKs some RLINKs definitely have to be changed, because only the last, you're not going to have a linear list if some of the intermediate RLINKs are.
We have to physically change the bits of those RLINKs in memory, but we're not changing the fact that this is a linked list connected by RLINKs. We don't have to chop it up the way that figure 26 is chopped up with nulls in some of the RLINKs until the very end, or even not at all, as I said. Right?
Okay.
We can leave it as
I like the not.
And just
I like the not at all. I like the observation of not at all because, like you said, it's either.
Michael, you're cutting out, I think, because of the phone ringing, but.
Can you hear me now? Yeah.
Well, okay, better.
Well, what I like the observation that you can tell that RLINK is not supposed to be there because the two parents are different. So if you have your RLINKs, can you make a whole list out of that? A whole link list? Probably, yeah, sure, why not?
Yeah,
sure you can.
So you just need to get the nodes.
That's probably how you solve this problem.
Maybe. Well, so the trick is you need to get the nodes into level order. And we know how to sort a linked list because we've done merge sort. So we can sort a linked list. And we also saw way back, one of the interesting things Knuth had to say about sorting is that if you sort the books on your shelf by, author, all of the books by the same author wind up together. So if we sort our linked list by parent, all the, just by the address of the parent, right, then all of the siblings wind up together. But the problem is that doesn't mean they wind up in level order. That doesn't even mean we wind up with the roots at the beginning, right? Maybe we wind up with all the roots at the end, and then level 3 and then level 1 and then level 2.
Does that matter?
Well, it does if we're going to then use that to go on to
you need the root as the first one, but the rest don't matter.
So if you're asking whether
the parents together, but then we still have to figure out how to set the L childs appropriately. Wait, is that easy? Well, I guess that's that's immediately a quadratic time algorithm. So step 1 is sort by parent. That puts all of our siblings together. So that's
wait a minute. Hold on. Sort by parent, and the parent of the root is null, so you just put that one first. So you're sorting by parent, you already got your root at the first element.
Yes, but let's look at figure 26. What this will give us might be something like AD, and then EFG. K, and then J, and then BC, and then H. Right? So we put all the siblings together, but we have another step to do yet. But we can do that next step in quadratic time, because then what we'll do is we'll say, okay, for each of these, for A, for each node in the list, find out who its left child ought to be, which means walk through the list until you find someone whose parent is that node, and then once you do, set L child going the other way. We don't even need to do that. That's not even quadratic time. Hey, there we go. This is linear time. So what we do, we walk through each node in the list, and when we get to the beginning of a run of siblings, we know its parent, and we link up its parent's L child to itself. Boom. Okay, so here's what we do. Step 1 was sort by parent. So that gave us like, and I'm going to write this down. So that gave us like, let's say A, D, E, F, G, K, J, H, B, C. All right.
So are you thinking of using something like a link merge sort on this? You're using the RLINKs?
Yeah, we just do like a merge sort, which we've done before. And then I'm going to walk through this, and I can tell when I'm at the first element of a range of siblings, right? Because the parent node changes. So we can mark down that we know the siblings. So then I say, okay, for A, look at its parent. Oh, it hasn't got one. Okay, cool. Let's go on to the next set. Then we look at E. Look at its parent. What is E's parent? E's parent is D. So let's set E's, or so E's parent is D. D's L child then is going to be E. And then we keep going on. So we did E, F, G. Those are all siblings. Then we get to K. K's parent is C. Therefore, we draw a line from C to K. Because we already had K's parent was C, so we can get from K to C quickly, and then this is just bringing us back. And then J. J's parent is F. So F's cell child is J. H. H's parent was E. B. B's parent is A. C has the same parent as C, and then we get to the end, and this is what we ended up with. And that was n log n to do the merge sort, and n to link up the L childs after that.
Is the sort necessary?
We need to get EFG together somehow. So maybe not, but something has to happen. Because EFG are not naturally together. And together, these are in RLINK order, right?
They do have the same parent.
Right, that's why sorting by parent puts them next to each other. Yeah. But if we don't sort by parent, we have to do something else to get them next to each other, and I'm not sure what that would be. But that's still a lot more efficient than I was worried it was going to be.
Yeah, yeah.
All right, I'm looking at the answer now.
All right.
26. And he gives it as an algorithm, of course. And it does not look like he is sorting anything. Okay, this smells like he's got a linear time algorithm. This is exercise 6, right?
I have a feeling the fact that he's mentioned that it's an oriented forest where order doesn't matter.
Well, order can't matter because we haven't got the order, right? We only know the parent links.
Yeah, so I guess he's just excluding that sort of additional requirement.
Yeah, we can't put the children in the right order because we have no idea what the right order is.
Yeah. Okay, this was great. So we will meet next week, as I mentioned. And yeah, thanks for attending. Bye-bye.
All right.
Thank you, Sir Taj.
You're welcome, Michael. Bye.